Okay, hello everyone, welcome to 130B, Quantum Mechanics. So we will continue our lecture today. So today I'm going to continue talking about harmonic oscillator, and then I want to introduce you to a new method to solve the eigenspectrum or eigenenergy and eigenlevel of the harmonic oscillator Hamiltonian, which is called quantum bootstrap. This method was only invented 3 years ago. So you don't find it in any textbook. But I think it's a good method because in many of the textbooks, if you try to read about harmonic oscillator creation and annihilation operator, there is not a very clear argument why this energy level must be discrete, must be integer. There's some hand-waving argument, but not very convincing. But today we will see some very convincing argument for that. So to start, let me first review what we have learned so far. We start from, we want to study this Hamiltonian, which is made of position and momentum operator. It is also called the quadratic form of the Hamiltonian because the Hamiltonian is this quadratic polynomial of position and momentum operator. Position and momentum operator has a non-trivial commutation relation like that. So that's the definition of the problem. And the goal is to find the eigenspectrum of the Hamiltonian given this non-trivial algebraic relation. We can see this is our only starting point, and just starting from there, we can derive the full spectrum. Based on that, the first step is to define annihilation and creation operators by combining position and momentum operator. And because of the non-trivial commutation relation between these two operators, there's also a commutation relation between creation and annihilation operator. More precisely, this relation tells us how to commute one operator through the other operator. Furthermore, we can define another operator which is called number operator, which is made of a creation operator times annihilation operator, means that you first annihilate and then create. This new operator also has its own algebraic relations. But interestingly, this new operator, the reason to define that is it helps us to simplify the Hamiltonian. It turns out the Hamiltonian can be rewritten in this form such that we only need to understand the spectrum of this newly defined particle number or number operator. And then in order to understand the property of number operator, we need to base on the commutation relation between creation and annihilation and try to derive how do we commute these operators through the number operator. And there's some formula there. And through those definitions and derivations, eventually we end up with a formula which tells us if we continuously do this annihilation m times and then do the creation operator another m times, by combining these operations, this whole operation can be nicely written only in terms of the number operator, but not as a single number operator, but as a product of this number operator and identity operator and so on, multiplied together. So that's something like that. And this relation is important because it plays an important role in quantum bootstrap. Quantum bootstrap is an algebraic technique to find this eigenspectrum for the number operators. It only relies on a very simple constraint in quantum mechanics, which is the positivity constraint, which says that for any state vector, if you take its norm square or the scalar product of the scalar vector with itself, this norm square or scalar product must be greater or equal than 0. And this simple idea, when you apply to these eigenstates, let's say, of this n operator, then we can say if this n operator eigenstate, which is labeled by ket n, is acted by any other operator, which is called O, we can show that it must satisfy this condition for any operator O there. And based on that, we can choose some very special case because although it must satisfy for all O, but we are not going to check that. The strategy is to use the least amount of constraints to get the most amount of information out of the system. So you don't want to enumerate all possible O's because there are all the possible operators in this infinite dimensional Hilbert space. There are infinite number of them. we actually choose a very special sequence of observables or series of operators, O, which correspond to the annihilation operator to the mth power. It turns out it is sufficient just by using these series of operators. You can obtain enough number of inequalities, and those inequalities will eventually determine the spectrum of the number operator. So how it works? Well, we will start from this construction, and then we substitute that into the positivity constraint. So if you have a to the mth power acting on this n state, if you treat that, the whole thing as a cat state, then the corresponding bra state is just by flipping this cat to bra and also changing this a to a dagger, just do a Hermitian conjugate of everything. So then this basically is the scalar product of a state with itself. And because of the positivity constraint, this product, this scalar product must be greater than equal than 0. But on the other hand, we also know that inside this scalar product, this operator a to the mth power and a dagger to the mth power has a formula. And that formula allows us to replace this creation and annihilation operator product into a product of number operators and identity operators. But because this n state is both an eigenstate of the number operator and the identity operator, number operator acting on this eigenstate gives you the eigenvalue, which is denoted as n, and then the identity operator acting on the eigenstate, acting on n states. Actually, any state is an eigenstate of identity operator, so the corresponding eigenvalue is 1. So that's why you replace this identity operator by 1 and replace this number operator by n, and then this product basically becomes n minus l, and then product over all the l goes from 0 to n minus 1. So this is how we evaluate this inner product or scalar product, because using the eigen property. And this product, if you write it down, it's like n times n minus 1 times n minus 2 times all the way to n minus m plus 1. So you can also rewrite it as a ratio of 2 factorials. Factorial n is a notation, which means if n is a number, you basically take this number times n minus 1 times n minus 2 all the way to 1. Suppose n is an integer. Yeah. But even if n is not integer, there's a similar function called the gamma function, which allows us to define factorial for non-integers. But let's not worry about that. This n factorial just means n times n minus 1 all the way towards 0. And then this n minus m factorial has the similar meaning. You start from n minus m, and so it's like n times, on the numerator, m times n minus 1 and so on. But on the denominator, it goes like n minus m times n minus m minus 1. Because at one point, it will reach n minus m. So then the numerator and denominator, starting from there, they will be identical, so they will cancel. So what is left over is n multiplied all the way to the last term. The last term here, the last term will be n minus m plus 1. So that's exactly the product that we wish to compute in the front. Okay, so that's just another way of writing it. Okay, so the positivity constraint basically means that this scalar product, as I show up there, must be greater than 0. But this product basically becomes this number, and then all these numbers must be greater or equal than 0. So what does it mean? It actually corresponds to a series of inequalities. Each inequality is labeled by an integer m. And this m goes from 0, 1, 2, and so on. When m equals 0, let's see, when m equals 0, this product doesn't even become effective because L cannot be product over 0 to minus 1, right? There's no such a product. So what happens here is basically 1 greater or equal than 0, because if you are not producting anything, then the initial condition for the product basically is 1. But if that's a trivial case, that inequality doesn't tell us anything new, because that's always hold. What about m equals 1? If you take m equals 1, this inequality must also hold, but in that case, that's L goes from 0 to 0, so there's only one term, which is n greater or equal than 0. When m equals 2, that is n times n minus 1 greater or equal than 0. So you have all these inequalities that gradually goes from n to n times n minus 1, and then times n minus 2, and so on. So because when we derived this equation, we didn't put any constraint on m. So this inequality is supposed to hold for any m, any positive integer m. So all these equations must hold. I have a demonstration here. So if m equals 0, let's take a look. So this black line corresponds to the, let me explain what I'm doing here. Maybe a little bit, yeah, anyway. So the horizontal axis is n, and the vertical axis is this scalar product we just calculate, which is also the product of n. And then when m equals 0, this equation basically means, basically this quantity is basically 1. So I'm drawing 1 here as a function of n, meaning that independent of n, it is constantly 1. And 1 is always greater or equal than 0. So the feasible region for this eigenvalue n will be the full real axis if you only consider m equals 0 condition. So that doesn't bring you anything more. But now you consider m equals 1. Let's take a look. M equals 1 meaning that n greater than 0. So this black line is trying to draw the function on the left-hand side, this n. So n as a function of n is a straight line that going through the origin and then with a slope 1. So this straight line, when it goes through the origin, it becomes negative on the negative side of this real axis. And then it's positive on the positive side. This just means that n must be a number which is greater or equal than 0. So all the region that is below this line, when this black line is positive, that corresponds to the feasible region. When this black line becomes negative, it's not feasible. So the feasible region now gets restricted to the positive real axis, and also including the origin. That's very important because it's greater equal than 0, not greater than 0. So the origin is also included. So let's now add another condition to that. That's based on this feasible region and add a new condition which n times n minus 1 greater than equal than 0. And let's take a look what this function looks like. So this black curve, again, plots the function that corresponds to this n times n minus 1, because this is a quadratic function and has two roots. One root is n equals 0. The other root is at n equals 1, which is these 2 points, right? So if you want to pass these 2 points through the real axis, and the only quadratic function you can draw is something look like that. And then by saying this must be greater or equal than 0, that means this quadratic function is the feasible region, which actually corresponds to all the green region and green region here. But we need to remember that previously, when we imposed the first two conditions, m equals 0 and 1, we already restrict our feasible region to this region of positive real axis. So we need to add new inequalities based on that, but we shouldn't violate the previous inequality. So we need to further restrict our feasible region to these regions. So this region will correspond to n greater or equal than 1, and also there's an isolated point which is at n equals 0. Because that point, although it's a single point, it was included in the previous region, and it was not excluded by this new inequality yet. So it is still there, okay? So we get a single point there. So the region basically gets disconnected. And now let's go to look at this, another equation, the fourth equation, which is labeled by m equals 3. And then if we click that, we will find its curve. On the left-hand side is n times n minus 1 times n minus 2, basically correspond to a cubic curve, which goes through these 3 points, basically. And then this cubic curve has such a shape that it only becomes greater or equal than 0 in these green regions. So that means it allows us to take values in these green regions. But we still shouldn't violate the previous inequality. So again, it will further restrict the previous feasible region. Let's take a look at the previous feasible region. Is this dot, this point, combined with that region. But now, with the new constraint, it becomes this dot combined with the remaining region. So now the rule becomes very clear. Now you just continue cranking up your number m. For example, go to m equals 4, and then you will find that all the feasible region gets further constrained, and then go to n equals 5, and then go to n equals 6. So once you go to all, you just crank up this inequality order and order higher. If you go through all the possible inequality, what you will find is that the feasible region of the value n gets constrained to such a discrete isolated points. And all these isolated points just happened at the integer positive, or let's say natural numbers, non-negative integers, okay? So that's why this quantum bootstrap, at the beginning, it is just a very simple principle saying that for any state, if you inner product with itself, the scalar product must be greater or equal than 0. But if you can evaluate this scalar product using all these algebraic relation that we derive, eventually we end up with a series of inequalities. And these inequalities turns out to be so powerful that it leave no room for the choice of a value of n. It basically tells you that n as an eigenvalue of this number operator has to take values in has to take discrete values of natural numbers, which goes like 0, 1, 2, 3, and so on. So, so this is the idea of quantum bootstrap. Is that any questions? Okay. So, so the conclusion is like this. First of all, the eigenvalues of the number operators are discrete, and for this reason, this operator n hat is called the number operator because really counts the number of something. And then this something, we give it a physical meaning, we call it a particle, it's a boson. So it counts the number of elementary excitation in the system. And the reason that it's an excitation because indeed, when this n is larger, the energy of the system is also higher, so it corresponds to exciting the motion of this harmonic oscillator. And when n equals 0, there's a corresponding state, which is the 0 cat state, which is also called a vacuum state because it corresponds to a state with no boson excitations. And then it is also the ground state of the harmonic oscillator Hamiltonian. The other eigenstate, which goes as cat n for n equals 1 and 2, are excited state of the Hamiltonian, describing the state where there are n bosons occupying those oscillation mode. So we need to distinguish two concepts. One is the oscillator. Oscillator is something that is oscillating there. And throughout the whole argument or derivation in the whole system, there's only one oscillator currently. So that's also called the oscillator mode. That is like a mode where the boson can occupy it. But this single mode actually can be occupied by many, many bosons, which means that there's only a single oscillator in the space, in this one-dimensional space that is oscillating. But for that, you can already occupy many bosons, and each different boson number corresponds to an eigenstate of that motion of that oscillator. And the more bosons there are in the system corresponding to the fact that there is higher energy injected into the system, that the oscillator is oscillating with a larger amplitude. It's like that. So there's a single oscillator corresponding to a mode which can hold multiple bosons. So that's the idea between the difference between oscillators and bosons. And bosons basically describe the elementary excitations of that single oscillator. And that boson is an emergent particle in the system. So you can imagine if you have multiple modes, for example, if you have a sound wave in the solid, which has actually multiple modes labeled by different wavelengths, then you can have multiple different bosons, which are phonons, actually propagates in the solid. Okay, so, so that's what I want to say about how to solve this harmonic oscillator Hamiltonian, and then we can see that using quantum bootstrap, we automatically obtain this conclusion that energy levels are discrete, and the energy level spacing in this case are equal. There's even spacing. Okay, so now we are going to talk about the next topic, which is about how to connect all these eigenstates. So we have just talked about that the eigenvalues are natural numbers. That's very good, but we still don't have much understanding of the eigenstate. It seems to us that eigenstate at this stage is just very abstract notations, which labels those states that correspond to the eigenvalue. It's better if we have a further understanding of them. So one conclusion that we can already reach is that because all these eigenstates are labeled by different eigenvalues and of a Hermitian operator, and what we have learned previously for Hermitian operator, different eigenvalue labels orthogonal states. As long as the two state has different eigenvalue, then the two states will be orthogonal to each other, meaning that the scalar product will be 0 if n doesn't equal to n prime. But when you overlap the state with itself, it is always a good convention to assume that the state is normalized. Every cat state labeled by this n is normalized, so such that they form an orthonormal basis. And then that means the inner product or scalar product has this delta function form, or chronic delta symbol form. Okay, so that delta symbol basically means that it is 1 if n equals n prime, and it is 0 if n doesn't equal to n prime. And this form an orthonormal basis. And this basis actually, it's an infinite number of bases, infinite set of bases. And then this infinite set of bases is called Folk state basis because it was proposed by Folk. And then, or people also call it boson number basis. I think that's a more straightforward name. So this forms an infinite dimensional Hilbert space spanned by this basis, and then in this space there's a resolution of identity again. The identity operator in this space can still be written as a projection operator of each eigenstate and then summing over all of them. Okay, so that identity resolution allows us to decompose, for example, different states into the number basis, boson number basis. Okay, so this is the definition of this eigenbasis of the number operator. They actually forms a complete set of orthonormal bases for the whole infinite dimensional Hilbert space of a harmonic oscillator. But we are more curious about how to connect all different states. So that's what I want to talk about in the following, that if you can show that previously we say this A corresponds to annihilation operator, A dagger is creation. But we didn't explain why do we name it in this way. So now we already establish the intuition that this n state correspond to a boson occupying, n boson occupying the harmonic oscillation mode, that kind of n particle state. So then, given that intuition, we can actually show that if you apply this A operator on that state, that gives you a new state. And that new state will be a new eigenstate of this n number operator with a different eigenvalue. The reason is that previously we have already derived if you commute the annihilation operator through the number operator gets -1. But if this state is an eigenstate of this number operator, then this operator hits this state, basically gives you the eigenvalues. So the eigenvalue is actually n-1. So if you look at this equation from far, what happens is that there is a state which is called A dagger acting on n. You treat that as a whole, as a state. Now you apply this number operator on that state. What happens is that that state doesn't change. And the only thing that happens is that there is an overall factor, scaling factor, appearing in front of this state. So we can only conclude that this state must be an eigenstate of this n operator with eigenvalue n-1. But we already have a notation for eigenvalue n-1 state, which is this state, right? So we must conclude that if we apply the annihilation operator on the state n, it must give us something that is at least proportional to the eigenstate. So this is supposed to be the eigenstate which is normalized. But this is actually also an eigenstate, also with the same eigenvalue. But we cannot guarantee its normalization because we haven't proved that it's normalized. So the n state is normalized. n-1 state is also normalized. But maybe A acting on the n state will give you something that is proportional to n-1, but not necessarily equal to n-1. Because any eigenvector, if you have some proportionality, maybe I can just write it like that. It is proportional to n-1, meaning that there is an unknown coefficient c in front of that, something like that. So in order to determine this this unknown coefficient in the front, what you can do is to calculate the square norms of this operator. The reason is that by calculating that, essentially what we are doing is that, maybe let me make a copy, and what happens is that if A acting on the n state is c times n-1, you can really replace this A here by c, and then this will be n-1. The other A dagger acting on n, because that's just the broad state correspond to the cat state. So what happens is that the c will get a complex conjugate, and then this n will become n-1. So we are just using the assumption which we have already shown previously, A acting on N is an eigenstate of eigenvalue n minus 1. So it must have this form. And this form basically indicates that C star C. And then will be actually, if you follow this algebra, A dagger A will become an N operator, but N is also is also give you an eigenvalue, so nothing is left over. You basically get this number N, which is the eigenvalue. But on the other hand side, what you get is C star C, because n minus 1 eigenstate is also supposed to be normalized. So, so the whole derivation basically leads to an equation. On the left-hand side is C star C, which C is the coefficient, undetermined normalization coefficient there. And then on the right-hand side, there is a single number N. So the simplest solution is to choose C to be square root of N. Of course, C can also be square root of N followed by any phase factor, let's say, and because phase factor doesn't affect this norm square of this complex number, but it is then up to human choice. It is a convention in the community that we always choose the positive root of this N, basically. So then we reach the conclusion that C must be equal to square root of N. So if we substitute that there, that gives us a relation that tells us when you apply this A operator on the number eigenstate, on the n boson state, it gives you a n minus 1 boson state. But there's something more. Apart from getting that state, there's also an amplification factor. That state is not just getting n minus 1 state. It's getting n minus 1 state multiplied by a factor, and the factor is proportional to square root of the boson number in the system. So that is the way that the annihilation operator must act on the system. And then there's no other room, not much room to move these pieces, because everything is derived from this algebraic relation, and it has to be like that. And following the similar derivation, which I show in the second line, you can also find that if you apply A dagger on this n boson eigenstate, you get an n plus 1 eigenstate with a prefactor. And the prefactor, instead of square root of n, it's square root of n plus 1. Okay? Any questions? And based on that, we can even define this number operator eigenstate, n boson state, starting from the vacuum state. Because if I start from the vacuum state, I can keep applying the creation operator. So now the meaning of creation and annihilation is very clear. Annihilation operator acting on an n boson state annihilates a particle. Creation operator creates a particle. But we also need to take care of the fact that there is also a non-trivial scaling factor in the front. So following that principle, we can, in principle, start from this the vacuum state, right? We can apply the creation operator. We can get 1 particle state, and apply the creation operator again, getting 2 particle state, and so on. So if you start from the vacuum state, applying the creation operator on the vacuum state gets 1, and then applying this creation operator on 1, what you get will be square root 2 of 1, and then followed by 2. Yes, square root 2 of 2. So that's the equation, right? If you A dagger further applying on 2, you will get square root 3 multiply the 3 states. So that means if you keep applying this A dagger operator, for example, A dagger, and A dagger operator, if you apply them 3 times on the 0 state, you will first get 1, following by A dagger, and then you will get all these. Basically, you will multiply all these together. I will just write down the result. So if you start from the vacuum state and apply the creation operator 3 times, all these prefactors has to be multiplied together into a 3 factorial and then square root, right? Square root of 1 times square root of 2 times square root of 3 is square root of 1 times 2 times 3. 1 times 2 times 3 is 3 factorial, is 6 actually. So there's a factorial factor there. And then that basically means that the 3 states, 3 particle states can be written as A dagger acting on the vacuum state divided by square root 3. And that actually generalized to any particle. So in this way, we basically has established what are these eigenstates. Although it's still not very intuitive. Maybe there's not a wave function yet. But already we can build all these eigenstates all from the single state, which is the ground state. As long as we know the ground state, we can keep applying the creation operator on the ground state, and that takes us to all these excited states. Okay? So in some sense, we already get an expression for what these excited states should be, right? You can, whenever you see all these excited states, you can replace it by this definition. So everything boils down to how to evaluate all these operators on the ground state, okay? So that's what I want to say about the algebraic method. For harmonic oscillator, let me go through this summary very quickly. Let me remind you that there is a linear relation between position momentum and creation annihilation. Creation annihilation operator is just certain kind of linear combination of position and momentum operator. And the other way around is also true, because if you can combine them into these two operators, you can recombine this creation annihilation operator back to the position and momentum operator, and that is the formula for that. The fact that there is a non-trivial commutation between position and momentum leads to the commutation relation between creation and annihilation. That actually tells us how to commute operators through each other. And then it's very important to define a number operator, and given that operator, it has because either creation nor annihilation operator is a Hermitian operator, so we can't really quite talk about it's it's just I don't want to talk about their eigenspectrum yet, because their eigenvalue will not be real number, it will be more complicated. And it's easy to talk about the spectrum of this number operator, and it's also related to our ultimate goal of understanding the spectrum of the Hamiltonian. And it turns out that the spectrum of this number operator must be discrete, and then its eigenvalue must take all the natural numbers. Not only that, we also find that there's this creation annihilation operator really connects different eigenstates by annihilating or creating particles. And it turns out the harmonic oscillator Hamiltonian can be rewritten in terms of the number operator that automatically tells us that all the eigenstates of this number operator, which denoted as cat n, are also eigenstates of the Hamiltonian with eigenenergy like that. So this established the fact that the eigenenergy of Hamiltonian of harmonic oscillator must be discrete and evenly spaced. And that is what we learned previously, I think. So in doing all this, we never solve any differential equation or try to diagonalize any matrix, but it is the power of this algebraic method or quantum bootstrap that allows us to reach all these conclusions without solving equations. Okay, so in order to exercise this, in order to practice this, what we have learned about quantum bootstrap, I'm giving you homework 1 for part 2. So there will be a part 2 homework 1. So the idea is trying to give you a place where you can practice this bootstrap method to determine eigenvalues and eigenstate of a Hermitian operator. You can see I'm describing this problem in a very abstract way. I didn't write down what is this Hermitian operator supposed to be a matrix, right? But I didn't write down this matrix, so you don't know how to, how to write down a matrix and diagonalize that. You have to rely on the algebraic relations. So there is a Hermitian operator which we call the beta. Beta is Hermitian, meaning that beta dagger is beta. And there's another operator which we call alpha. I think there's a typo in the previous lecture notes, which I call it R, but it's alpha. Okay? So alpha and beta acts in the same Hilbert space and has the following algebraic relation. So this alpha is not necessarily Hermitian, so that's why alpha and alpha dagger are not the same. But beta is Hermitian, so beta and beta dagger is the same. So they have the following 3 algebraic relations. One is their commutator looks like that, and then if you take alpha dagger alpha, you can rewrite it as beta. So in some sense, this alpha is like creation, is like annihilation operator in the harmonic oscillator case, and then this beta is like the number operator. But you can see that this algebraic relation is not the same as harmonic oscillator. For example, for harmonic oscillator, alpha dagger alpha should be defined as the number operator, then it should equal to beta, right? And then here you see it's not equal to beta, it's equal to 1 minus 1/2 beta times beta minus 1, such a strange expression. But this is just a little bit more complicated than harmonic oscillator, but the relations very, in some sense, very similar. So you just need to follow all these steps, and then eventually I think we can reach wonderful solutions. You can show that you can actually find all the eigenvalues for this beta operator. So the first step is try to prove some of these commutation relations, and then you will be able to use this commutation relation and also do this exercise, try to calculate a dagger to the mth power and a to the mth power. So you already know when m equals 1, this is the starting point. So you need to start from there and then compute m equals 2. The m equals 2 case is you further sandwich this expression by a alpha dagger alpha from left-hand side, from left and right. But then you can use all these commutation relations that you derive in this first step and then try to do some simplification on the right-hand side. And then you will find that there's another very nice recursion relation that allows you to reach a conclusion for that. Okay, the conclusion will, the final expression will also be very similar to equation 52, which is a product of a bunch of things, a product of a bunch of terms. And then now you can apply the positivity constraint associated to a dagger A, meaning that because we want to determine the eigenvalue or the eigenstates or an eigenvalue of beta, so you need to assume that this beta operator as a Hermitian operator has a set of eigenbases with this eigenvalue beta, with beta belongs to real. So now you can do, what you can do is you can evaluate this beta, a dagger to the mth power and alpha to the m power alpha to the, and then beta. You evaluate this one will be greater or equal than 0, okay? So this one will be greater or equal than 0. And then inside this scalar product, this operator, I think you can evaluate in the second step, and then you substitute into this inequality, and then this inequality will give you a lot of constraints. And those constraints will eventually tells you what are the possible value for beta, because this eventually will be a function of beta, which is what you want to derive. And then eventually becomes a set of constraints like that. This function also depends on m. So there are m. For any m, there's this inequality. And based on all this, you can try to compute the eigenvalue. Not only that, you can continue to study how, when we act alphas on the eigenstate of beta, similarly, it will create or annihilate or raise or lower the eigenvalue, and then eventually connects all the eigenstate together. So in that case, we can actually write down the matrix representation for basically alpha and beta. I can tell you that in the end, if you do everything correctly, this Hilbert space is not an infinite dimensional Hilbert space. This is actually a finite dimensional Hilbert space. There's only a finite number of states in this Hilbert space. So that's why you can really write down a finite dimensional matrix representation for alpha and beta. After you finish all this, you can try to substitute your answer, because if you are not sure whether this answer is correct, because once you represent them as matrix, you can just substitute those matrix here and then verify that all these algebraic relations that we assume from the beginning are all satisfied by your final solution of this matrix representation for alpha and beta. Okay? Any questions? This seems to be a very difficult problem, but I think it was trying. Yeah. You can discuss with your peer students. You can discuss with TA. You can search online, but I believe there's no solution for this problem because no one has ever thought of this problem before. So, yeah. Okay, any questions about the quantum bootstrap method and this homework? Okay, very good. So let's move on. So previous quantum bootstrap methods already established that there are a lot of eigenstates of the number operator, which people also call it Fock states, or boson number eigenstates. Fock states are labeled by this 0 boson, 1 boson, and 2 boson, and so on. That's the idea. But as the state, we know every state can be represented as a vector. So again, we wish that we can write everything down as a vector. And then the idea to encode all these states is still use the one-hot encoding. So the no boson state actually corresponds to an infinite dimensional vector where the first element is 1 and the remaining elements are all 0. Because the first element corresponds to no boson state, second element corresponds to 1 boson, and this is 2 boson state, and so on. The fact that you are putting a 1 there, meaning that that element is chosen, or that state is chosen. So it's like checking the boxes. So you put a check there, that means this is a 0 boson state. If you put a check at the second place, that's a 1 boson. And if you put a 1 there, it's a 2 boson state. So these states are just one-hot vectors. You can encode them in this way. Although this vector encoding already has nothing to do with the wave function that we previously talked about. So the Fock space representation actually corresponds to a new set of bases different from the position eigenbasis. So now we are talking about the number operator eigenbasis instead of the position operator eigenbasis. They are actually not the same. So in the number operator eigenbasis, all these states, harmonic oscillator wave functions, no longer looks like a wave function. You can see this is a ground state, first excited, second excited state. Previously, maybe you have learned that the ground state of a harmonic oscillator has a wave function which looks like a Gaussian. So this state vector looks nothing like a Gaussian. It's completely not obvious. But again, this is the idea of quantum mechanics. You can use different bases to describe the same physics. It is just yet another set of bases that describe actually the same set of states. But now we can compute the matrix element for the annihilation and creation operator. For example, if we want to compute the matrix element of annihilation operator in the mth row and nth column, that will correspond to applying the annihilation operator on the boson number state n, and then project to another eigenstate, which is labeled by m. But when you apply annihilation to n boson state, it becomes n minus 1 boson state with a new prefactor n square root of n in the front. But now these two eigenstates see each other. But these eigenstates actually, as we already discussed, they form an orthonormal basis, which means that they are non-zero if and only if m turns out to be n minus 1. So that means if you try to write down this matrix, the matrix will only have non-trivial, for this A dagger matrix, only have non-trivial matrix element if the row index is the column index minus 1. N is the column index here. M is the row index here. And only if they are equal, only if the row is the column minus 1. So if the second column, then it's row 1. If you go to the third column, you go to row 2, something like that. And then apart from that, you also need to have a square root n in the front. So it goes like square root 1, square root 2. You can, maybe I should call it zeros column, first column, second column. And this is the zeros rows, first row and second row. Then that will match the index we have over there. And then you can check that this is exactly the matrix. Everything everywhere else where I didn't put any matrix element, those empty space correspond to 0, basically. And this is the matrix of annihilation operator. So annihilation operator really takes the 1 particle state to the 0 particle state, takes 2 particle state to 1 particle state, and so on. So you can see it's a off diagonal, but it's just side by side on the plus 1 side of the diagonal. It's like the first off diagonal line. And then this A dagger will be the negative 1 off diagonal line, which also has this form you can derive from there. And then by this matrix formulation, it's very obvious that A dagger is indeed the Hermitian conjugate of A, because what these two matrices are related by transpose followed by complex conjugation. And here there's nothing to complex conjugate. All the matrix elements here are real. So all we are doing here is just transpose. And now we can say, okay, so A dagger and A previously is quite abstract. Now we have something we can operate. It looks like a matrix. Let's try if we take A dagger and A and we multiply these two matrices together, what do we get? And that means we put this matrix on the left and put this matrix on the right, and then we start multiplying them together. And if you do it as an exercise, if you try it out, you will find that the result is basically like that. It goes like a diagonal matrix now, and then the diagonal matrix element goes like 0, 1, 2, and so on. So that's indeed the number operator, and the number operator is diagonal in its own eigenbasis. Any Hermitian operator is diagonal in its own eigenbasis. And then the number operator acting on, for example, the 0 state. Remember, the 0 state corresponds to a one hot vector with a single 1 in the front. Then what happened is that it multiplied this 0 to that eigenvector. And then if you have an one boson state, which is a one hot vector with a 1 at this first, let's say, column, then when you apply this number operator on that one hot vector, you get also the eigenvalue out. Okay? So this is obviously, all these one hot vector are eigenvectors of this number operator. And on the diagonal line, it is these numbers correspond to the eigenvalues. So this is consistent with our understanding, but what is more interesting is now you can reconstruct the coordinate and momentum operator out of that. Because we know that originally creation and annihilation operator was defined as a linear combination of position and momentum operator, and like x plus IP or x minus IP. So you can recombine this operator to reconstruct this position and this momentum operator in this way. And then just following the matrix representation, it looks like that. So it's very non-trivial, right? It becomes more and more non-trivial. To have some fun, we can check whether the commutation relation is correct. So you can actually take these two matrices and then type it into Mathematica, and then you can multiply them together. So you can do x multiply p, you will get this matrix. And then you will do p multiply x, you will get this matrix. So now what is, you can see these two different ways of multiplying x operator and p operator is not the same, meaning that these two operators, they don't commute. But the non-commutativity, you can see, is only on the diagonal. There are some off-diagonal matrix element that's true, but you can see these off-diagonal matrix element that goes like square root 2, square root 6, and minus square root 2, minus square root 6 are identical between these two different ways of multiplying position and momentum operator together, but the only difference is on the diagonal. This is all 1, and this is all minus 1. This turns out to be the case. Yeah. If you really multiply these two matrices together, they have that form. And then given that form, one can show that if you take the subtraction, xp minus px, what is left over is on the diagonal. And that on the diagonal, what is on the diagonal is just a bunch of ones which correspond to identity operator. So in that way, you can really verify that it actually verifies the commutation relation that xp commutator is actually a bunch of ones multiplied by an overall factor I. Notice that there's a factor I in the front. Okay. Okay, so this is very reassuring, and then this means we are doing everything correctly, and then we can even restore our starting assumption that x and p has this commutation relation. So this operator, so this tells us a lesson that operator algebra itself is basis independent. The fact that x and p commutator is I times identity, that is true in the position basis. That is also true in this so-called boson number eigenbasis. Even though this boson number has no clear physical meaning associated with wave function and things like that. We are not talking about wave function now. But still, we can use a seemingly very different set of algebra to reconstruct this commutation relation out of that. So these algebraic relation, like how they commute, and then how you commute one operator through the other operator, what's the definition, what's the relation between these operators, those are universal. Those are, doesn't matter which basis you choose. So it is this algebra that the commutation relation is I times identity. That should be considered as a defining property of x and p. And the very concrete representation, whether you want to write x and p operator as these kind of matrices, or if you want to write x operator as multiplying x in front of the wave function, and writing p operator as applying a differential operation to the wave function, neither way, either way is fine. I think it's just different ways to represent the operator, and then their algebraic relation remains the same. And in deriving all these results previously, we actually only rely on the algebraic relation. So those are the universal properties of related to harmonic oscillator. And I want to also briefly comment on, okay, so sorry, that's it for today. Yeah, thank you.